Hello guys, nice to see you.
Good afternoon.
Hi,
Good afternoon.
good afternoon. How are you doing?
Fine. Thank you.
Good. Friday, end of the week. It should be good mood. Okay, so last time we derived equations for power and intensity, which is transported by sound wave, and considered also, so we did these derivations for some plane wave, which is formed in a cylinder. So it's kind of one-dimensional case. In a three-dimensional case, when we have some point source of sound located in isotropic environment, then sound is spread spherically in all directions. And when we deal with light intensity, we need to divide average power of the point source by area of a circle with certain radius, at which a distance from the source, which is equal to this radius, in order to get the light intensity, the sound intensity. So today we will continue our discussion of intensity of sound, but we will do it in a bit different approach. Means we will operate with level of sound, and further we will consider Doppler effect and forming of a shock wave. When we have a source of sound which is moving faster than the speed of sound in the given environment. Okay, so with let me maybe change to the screen so we can write already. Oops. The thing is that we could have operate with sound intensity in units like watts per square meter, and it's doable. We can do it, so it's not a problem. However, the range of sound intensities which our ears can detect is very broad. So it ranges from something, our threshold of hearing, let's call it I0, like intensity, the lowest intensity which can be detected by our ear. Something like 10 to minus 12 watts per square meter. Let us specify here, but we will come back to this point, at 1 kilohertz. So that is kind of important because our perception of sound and kind of estimation of its intensity by means of our ears depends on the frequency of sound. We will discuss this a bit later. However, this is some standard frequency, 1 kilohertz, at which we can quantify some parameters. So the limit of hearing is 10 to minus 12 watts per square meter. It's very, very low intensity. And of course, we can hear like more intense sound, and there are many orders of magnitude range of sound intensity which we can detect. In order to avoid working with such wide range of orders of magnitude, was proposed to deal with sound level. And sound level is measured in decibel. So it's some dimensionless, I mean, it's artificially created, this unit, just because we need to define it in something. So it is given as 10 multiply 10's logarithm intensity of the sound, which we detect, divided by this threshold intensity level. So technically, you see that it's dimensionless, but it used to be measured in decibels. So decibels shows how many orders of magnitude it is louder than the threshold of hearing. So now let's say if we remember that threshold I naught is 10 to minus 12, then we can consider some sound intensity which already appears as painful for human beings, and that is usually 1 watt per square meter. So if we now substitute instead of I in the numerator of the argument of this logarithm, this intensity of 1 watt per square meter. So let's see which sound level we'll get for this sound intensity. So 10 times logarithm. Then we have unity here. And here we have 10 to minus 12. So eventually we will get 10 times log 10 to 12. Means this part, what it will be equal? Any ideas? Properties of logarithm.
1.
Oh, can you repeat, please?
Is it 1?
No, it's 12. It's actually the power. Logarithm, 10's logarithm, it gives us the power to which we need to put our base, which is 10 for 10's logarithm, in order to get this number, and that is 12. So 10 multiply 12 will be 120 decibel. So 120 decibel is already painful feeling. It's very loud sound. And if, for instance, we consider this threshold of hearing, so we will put 10 times logarithm 10 to minus 12 divided by 10 to minus 12. So instead of 1 watt per square meter, we will put the minimum, the threshold of hearing, 10 to minus 12. Then it will be decimal logarithm of unity, and decimal logarithm of unity will be 0, because 10 in the power of 0 will give us unity. So if we have this equal to 0, then our sound level is equal to 0 decibel. So that is the threshold of hearing. So we cannot hear lower intensity sound, means 10 to minus 12 will correspond to 0 decibel, and everything what is more intensive, in many orders of magnitude more intensive, will be defined by other values of this level of sound, which is higher than 0. And you can see now that decibels, beta, changes from 0 to 100, say 120 decibel. And if we operate with sound intensity, we need to deal with something, sound intensity. We need to deal with something 10 to minus 12 to 1 watt per square meter. So obviously it is easier to operate with such range of numbers from 0 to 120 than with numbers in the range of 12 orders of magnitude. That's why it's widely used in engineering, like also in measuring sound. If you download some apps for measuring sound intensity, usually they are given in decibel, not in watts per square meter. So another thing which we need to highlight here is that actually our subjective perception of sound, because of the structure of our ears. So it has been shown that this minimum like threshold of hearing depends on frequency. So if we show here in decibels sound intensity, and here will be frequency of sound. So frequency of sound will be in semi-log scale. So here we will have something, let's say 20 hertz. So that is in hertz. Here will be something like 1000. And here, let's say, will be 20,000. So that is range from 20 hertz to 20,000 hertz. That's normal, like average human sensitivity to sound waves. We cannot hear sound waves with lower frequencies than 20 hertz and higher. So lower is called like infrasound, and higher frequencies than 20 kilohertz is called ultrasound. So those frequencies are beyond our detectivity capabilities. I mean human ears. However, as you remember, I mentioned earlier that the threshold for hearing, here we can put 0 decibel. This is the lowest intensity which we can hear, is 10 to minus 12, which corresponds to 0 decibel at frequency 1 kilohertz. So at this point, 0 decibel is what we can barely detect. However, that is true only for 1000 hertz or 1 kilohertz. If we go to other frequencies, we will see something like this. So it goes to this and increases further. So it has this minimum around 1 kilohertz. And then in order to hear some frequency, let's say, I don't know, 100 hertz, we need intensity of this sound way higher than intensity at 1000 hertz. So that is the feature of our airs. And we have some perception since dependence of on frequency, and for different frequency of sound waves, we need different minimum intensity in order to detect this sound wave. So if we come to intensities, to frequencies lower than 20 hertz, for instance, then doesn't matter what intensity will be of the sound, we still will not be able to detect it. And that is also true for sound waves with frequency beyond 20 kilohertz. So here somewhere we have this highest sound intensity, 100 decibels, which we can accept in terms of loudness because it already becomes painful. What is interesting that this our sensitivity to extremely loud sound is frequency independent. So if we have low sound, we deal with threshold of hearing, then we have this dependence on frequency, which we show on this plot. So it goes to minimum at 1 kilohertz and increases in both directions for higher and lower frequencies. However, if sound intensity is very high, let's say, which corresponds to 120 decibels, which already at the level when it becomes painful to deal with such sound, then this dependence becomes flat, means frequency independent. So it doesn't matter if we have sound with 100 hertz or sound with 5 kilohertz, if its intensity is something like 1 watt per square meter, which corresponds to 120 decibels, then we will feel it equally. So it will be equally loud to us and equally disturbing and not comfortable. So this is some perception features of our airs, and in general kind of useful to have an idea how it works. Okay, now at this point we can stop discussing the intensity or sound level and switch to such interesting effect as Doppler effect. So let's say we have some one-dimensional case. So this is some axis X. We have observer and sound source. We can consider if observer is moving towards the sound source, means along axis X, then the velocity of the observer will be positive. If it moves in opposite direction, then velocity of observer will be negative. Similar, we can specify also to the source. So if it moves along axis X away from observer, then velocity of the source will be larger than 0. So this is this direction. If it goes in opposite direction, then Vs is smaller than 0. So that is some reference now. And we will obviously deal now with not with stationary, but mobile observer or source, or even both of them can move simultaneously. So it appears that frequency of the sound which we hear will depend on the direction and speed of mobile observer or sound source. So let us consider first mobile observer. So let's say sound source has the following features. We have some frequency of sound source, F. Then we have also corresponding wavelengths, lambda, of this sound. And we have sound speed in the environment, which is V. So we have these parameters. We remember that frequency is given as the ratio between sound speed and wavelengths. So now the question, which frequency will stationary observer hear if the source is approaching the we consider now mobile observer and stationary sound source. So which frequency will mobile observer hear if it approaches the sound source, which is stationary? So that will be some frequency f prime, which will be equal. So we need to consider that sound travels with some speed v towards observer from stationary source, but also there is some speed of observer in the direction to the source. So we need to add up these two speeds. That will be speed of sound plus speed of observer divided by lambda. So lambda is a wavelength which is generated by the sound source. So since we have a relationship for lambda, which is equal to v divided by frequency, we can substitute now this lambda with its expression. So we can write that frequency which we mobile observer hears will be equal to v plus v naught divided by v, and that will be multiplied by initial frequency of the sound. So we see that our numerator is larger than our denominator because we have v plus v naught. So if our observer moves toward the sound source, v naught will be positive, so it will be larger than the denominator, means that the frequency which observer will hear will be always larger than the real frequency of the generated sound. If observer is moving backwards, like away from the sound source, then this frequency which observer will be V minus V naught, because this V naught will be negative. It will be in opposite direction of the axis X, divided by V times initial frequency, like real frequency of the sound. So F prime is kind of apparent frequency which observer here because of this Doppler effect. In this case, our numerator is smaller than denominator, and that's why frequency appeared will be smaller than real frequency of the sound. Okay, with this is clear. Let us consider the case when the the source is moving and observer is stationary. So again, the generated sound has some wavelength lambda. If the source is approaching the observer, then the apparent wavelength should be equal to lambda minus delta lambda. So it will be reduced because of approaching source to the observer. That can be represented as lambda minus V source divided by frequency of the sound. And that is kind of equivalent of change of wavelengths because of mobile source. Since lambda, we already mentioned that is equal to speed of sound divided by frequency, then the apparent frequency, which observer will hear, prime, will be equal to speed of sound, which is constant, divided by lambda prime, the apparent wavelengths. So then we can write that it will be speed of sound divided by lambda prime. It is given by this equation. So it will be lambda minus V source divided by frequency. Now, if we set to common denominator, we will get V divided by lambda times frequency minus Vs divided by frequency, and that will be V divided by lambda times frequency gives us speed of sound. So that will be V divided by frequency minus Vs divided by frequency. So we can take out of the parentheses F, and we will get V divided by V minus Vs times frequency. So now we have the equation which will tell us what will be the frequency of sound which observer can hear when the source is approaching the observer. So in this case, we have negative value for speed of observer because it moves towards the of the source, because it moves towards the observer in the opposite direction to axis X, which we define. And here we see that the numerator will be larger than denominator because we subtract. So V is in numerator. In denominator, we subtract something from V. So obviously it will be smaller. That's why frequency which observer will hear will be higher than the initial, like original frequency of the generated sound. So if we have a situation when the source is moving away from the observer, then f prime is equal to v divided by v plus v source, and times frequency f. So in this case, denominator is larger than numerator. We have f prime smaller than f. So the frequency of the sound which observer will hear will kind of be lower than the original frequency. Now, if we combine both options, when observer and the source of sound are mobile, we can write that the frequency which the observer will hear, the apparent frequency, will be defined by the following equation. So that is, so if, let us assume that both observer and sound source approach each other. So they go into that ways that they reduce distance between them. So in this case, it will be V plus V observer divided by V minus V source times frequency of the generated sound by the sound source. So with this equation, you need to take into account the signs of V naught and Vs, because for instance, if we have opposite case, let's say source and observer, they instead of approaching each other, they both move but away from each other, we need to change sign of V naught to negative and sign of Vs to positive. So there could be also a case when, for instance, observer is approaching the sound source, but sound source is moving away from observer. So they kind of move in the same direction along axis X, but with different speeds. So all these factors should be taken into account by appropriate signs for V naught and Vs, and then you can get the apparent frequency of sound which you can hear. So that is it with the Doppler's effect. And one more thing we need to discuss is a shock wave, which is formed by an object which is moving with speed higher than the speed of sound. That's another interesting feature of sound waves. So let us assume that our source speed is equal to 2 times sound speed, so twice higher than sound speed. And I'm sure you have seen this so-called Mach cone, like the front of shock wave, many times, but I believe that it's really good to draw it in the process of our discussion, so it will become more clear to some of you and will stay with you for long, this understanding where it comes from. So let us do it, and let us consider time interval within which we draw this situation, let's say 5 seconds. So that will be our axis X. This is where our source of sound starts at t equals to 0. So let us put here 0 second. So let us divide it to 10 equal segments. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so the length of each of these segments will be distance which sound can travel per 1 second. If that is the distance which sound can travel per 1 second, then at 1 second after beginning, our source, let's say plane, a supersonic plane, will be at this position. So it will be at 1 second. Because we have two intervals, since the speed of the source, of the sound source, is twice higher than the speed of the source of this sound, which is supersonic plane. Then, consequently, at 2 seconds, it will be here. At 3 seconds, the plane will be here. Then 4 seconds here. And at 5 seconds, finally, it will reach to the last point in this time interval which we consider. So it will be 5 seconds. Now, let us consider, assuming that this is sound, the environment is isotropic, so it's spherical distribution of sound. Let us consider that where will be the sound generated by this plane after 5 seconds. So it was generated at the initial position and until the end of our consideration, at the end of 5 seconds. This sound will have time which is equal to 5 seconds to spread in all directions. So that, let us put here axis y, and also put the same distances, like the same intervals here. So 1, 2, 3, 4. We need a bit longer. We can delete this. And here will be 5. We know that per each second, sound travels this interval. So that's why we will have some point here where sound will reach from this point, from the origin at 0 second. And here we also have 1, 2, 3, 4, 5. So this is another point where this sound will reach. So we can draw as much as it is possible some circle, and this circle will define the furthest points from the source at 1 second where the sound can reach in 5 seconds. So now if we consider point where this plane was in 1 second after the start of flight, it would have only 4 seconds until the end of our consideration. The sound will have only 4 seconds to spread. That's why it can travel only up to 1, 2, 3, 4 here. And here we also put like 4. 1, 2, 3, 4. 1, 2, 3, 4. So there we will have this circle. Then we go to point which corresponds to position of the plane at second number 2. And from here, it will have only 3 seconds to spread till the end, till second 5. So we have 1, 2, 3 up to here, and also 1, 2, 3 up to here. So it will be something like this. Then we have second 3. And from second 3, we have only 2 seconds for sound to travel. So it will be 1, 2 up here and 1, 2 up here. So that is this circle. Here will be second 4, and second 4, it has only 1 second. Point at second 4 has only 1 second to travel. So it will be up to here and up to here. So it will be such small circle. So now at point 5, it doesn't have any time to travel the sound because it's just generated at point 5, and we have our plane in the same point. So it just generated and had 0 seconds to spread in this environment. So now, unfortunately, it's not perfect, but we can see actually here, even with such poor drawing, that if we draw some tangential line to all these circles, starting from point at time 5 seconds, we will have something like this. So you see, it will be the line at which sound waves from points at each second will reach simultaneously. And that is the front of our shock wave, which is created by the supersonic plane. So here we can draw a similar line. So this cone is called Mach cone. And if we draw a perpendicular from point 0 second to this tangential line, so here we have right angle. Let's call it point A. This will be point B. This will be point C. So here at point B, we will have some angle alpha. So the distance from A to B, A, B, is defined as speed of ultrasound, like supersonic plane, like our supersonic source of sound, times time interval delta t, which is in our case, let's say 5 seconds. Then distance from point A to point C will be equal, AC will be equal to speed of sound times the same time interval t. So now, since we know this sides of the right triangular, we can write that sinus alpha this angle at the top of the triangle next to point B will be equal to AC divided by AB. That is equal to V times delta T divided by Vs times delta T. So we can cancel out this delta T, and that will be equal just to the ratio between speed of sound to the speed of our plane. And this can be given as 1 divided by m. So it's Mach number, so-called parameter, and this m is actually how faster, in how many times the source of sound is faster than the speed of sound. So that is Vs divided by V. So with this, when you know the speed of the plane, also the speed of sound, you can calculate m. If you know m, you can determine the angle at the top of this shockwave cone, and then it is possible to deal with some problems which are associated with the shockwave created by objects which move in the environment with a speed higher than the speed of sound wave propagation. Okay, we are running out of time. This is everything what I wanted to tell you today. Do you have any questions? Okay, looks like that everything was clear. It's quite simple material for today, but I believe that this explanation with the shockwave could be helpful to some of you guys to clearly understand where it comes from. Okay, then thank you for your attention. Have a good weekend and take care, and see you on Monday.
Thank you. Goodbye.
Bye.
Thank you. Goodbye.
Bye-bye.